Let's have a look at the problem from Putnam test 2001, problem A2. So which means it's a relatively easy one. So we're trying to find out the infinite sum, n from 1 to infinity, of 2 to this special notation here denotes the closest integer to square root of n, where n is a positive integer. So for example, square root of 2, roughly 1.4 something, closest integer would be 1. Square root of 3, roughly 1.7 something, closest integer would be 2. So we have to distinguish it from the floor of, for example, 1.7, that is 1. But in this case, the closest integer to 1.7 something is just 2. So if you use a calculator, you can realize the number of, for example, if we start from 2 square, next number is 5. 4, 5, 6, 7, 8, 9, 3 square. Right, any n square plus 1. N plus 1 square. Previous was n square plus 2n. You will realize that they're exactly first half of those 4 numbers. First half of those, for example, 2n numbers. Exactly, if you square root of 5 or 6, closest integer would be 2. Square root of 7 or 8, closest integer would be 3. Here, 2n numbers, first n numbers, closest integer of their square root would be n. Closest next n numbers, closest integer of their square root should be n plus 1. So regularly speaking, we want to prove it. When does the square root of n squared plus k is some positive integer? When is it closer to n, and when is it closer to n plus 1? Right, generally speaking. Right. If we let the distance between that point, square root of n squared plus k minus n, that distance, let it be smaller than that distance, n plus 1 minus square root of n squared plus k. So what kind of k make this inequality true? Right, so rearrange it, plus k, less than 2n plus 1. Right, both sides are positive, so square both sides. N squared plus k, less than 4n squared plus 4n plus 1. So 4n squared plus 4k, less than 4n squared plus 4n plus 1. 4n squared, 4n squared gone. K is less than n plus 1 over 4. So k cannot be a decimal, right? But it could be equal to n, that's fine. Less than or equal to n. Greater than or equal to 0. 0, 1, 2, 3, all the way to up to n. This kind of k makes the closest integer of square root of this type of number closest to exactly n. Likewise, if you want it to be closer to n plus 1, you just change the direction. So it comes out to be k is greater than or equal to n plus 1, less than or equal to square root of n plus 1 is equal to square root of n plus 1 squared. That's square root of n squared plus 2n plus 1. This k, this is what happens, right, when this is equal to n plus 1. So k equal to 2n plus 1, that's fine. Right? N plus 1, n plus 2, n plus 3, all the way to n 2n plus 1. This kind of k makes the closest integer to square root of this type of number closest to the integer of n plus 1. So far, we found out when k is equal to integer 0, 1, 2, 3, all the way up to n, that's when the closest integer to square root of n squared plus k is equal to exactly n. But when k is equal to n plus 1, n plus 2, or n all the way up to 2n plus 1, that's when the closest integer, the square root of such form, is equal to n plus 1. So to write it down in detail, we start from the n plus 1 perfect square. Don't worry about this one. Next one, plus 1, plus 2, plus 3, all the way. So until we reach the next perfect square, n squared, I say, between this number and this number, there are exactly how many numbers? Including those two numbers, we say we have this minus that. 2n minus 1. 2n minus 1 plus 1. 2n numbers, including those two. If we're not including these two, we have 2n minus 2 different numbers. Right? So first half, we have n minus 1 different numbers. So all the way up to plus n minus 1. This made from this number to this number. Right? Like I said, first half of the numbers, the closest integer to square root would equal to n minus 1. Right? Then next number would be this number all the way. So here we have n squared up to n squared minus 1. Right? Each of those numbers closest integer to its square root equal to exactly n is n. Next, n squared plus 1 up to n squared plus n. Right? From this number onwards, we have exactly n different numbers here. According to our conclusion, each closest integer of each square root of each is exactly n. Right? The next number onwards until n plus 1 square, their closest integer of each square root will be n plus 1. We don't worry about them. And we don't worry about these. Right? We just focus on from this number onwards up to this number. Right? Just so constant, consistently n. So when k is equal to from this number, right? Perhaps we expand this one out. So n squared minus n plus 1. So on and so forth, including this one, up to this one. That's when closest integer of square root of such form is equal to exactly n. Right? For some fixed n. So when you write down more details, like this, 9, 11, 12, 13, 14, 15, 16, 25, 24. Right? So it's just a matter of how we group it. Like I said, just fix some perfect square. Use its previous half numbers and its afterwards half numbers. Right? So you fix 4. Right? Between 1 and 4, you have 2 and 3. So you group from here. Right? From 4 onwards up to 9, you have 5, 6, 7, 8. Right? Take half of them, 5, 6. You group those. Right? From 3 square, that's 9, up to 16, that's 4 square. 9 and 16, you have 1, 2, 3, 4, 5, 6, 6 numbers. You group up to here. Then you group from here up to here. no. You 13. So somewhere in the middle of here, between 16 and 25, you have 8 different numbers. You group up to some number here. You have 16, 4 numbers. So 4 square. If it's n square, then you always have n. That's its closest integer to each of square root of each. So 3 squared. So always 3, right? You always 2, and those always 1. So here n is changing. 1, 2, 3, 4. All we have to do is work out. First, we sum from k from here all the way up to here. K from this number. So from this number all the way to this number. Inside you hear this k. K is changing, but top is constant. 2 to the power of n. Because if you fix some n from this number onwards up to this number, it's always n. That's its closest integer to the square root of n. Is always n. 2 to the always negative n. It's just k is changing. So here, first we fix n, then we sum with regard to n from 1 to infinity, right? That's the outer sum, right? First sum, second sum. Second sum is when n is changing from 1, 2, 3, 4, 5, all the way to infinity. Right? This is equal to 1. So we somehow turn this question into calculating this infinite sum. Right? First, inside here you have a finite sum. Then it's an infinite sum. So since here the benefit of this is that you have n as constant, you're only summing with regard to k, so you can just factor out anything that has something to do with n, right, out from here, plus negative. Then you sum with regard to k. N squared minus n plus 1. N squared plus n. That's 1 over 2 to the k. Right? That's just a geometric sum. So geometric sum, common ratio is 1 over 2. Right? Applying the formula, you have initial term is what? 1 over 2 to the n squared minus n plus 1. Right, that's the initial term. Then you 1 minus common ratio. 1 minus common ratio. How many terms here? N minus 2. 2n terms. So 2 to the 2n. So that is equal to n from 1 to infinity. In here we have 2 to the negative n times. Here you have half at the bottom. You flip it. Yeah, you have times 2. But 2 and this 2 to the power of 1, they can just simplify. Right, gone. Right, then you rewrite it as a 2 to the negative n squared plus n. Right, write it in this way, flip it. Then you multiply 1 minus, again, flip it. Write it as 2 to the negative 2n. Right, then you can multiply. So n from 1 into 2 to negative. multiply this inside here. 2 to the negative n squared plus n, negative 2 to the combined powers, negative n squared minus n. They multiply everything out. Right, so this multiplied by that, 2 to the negative n squared plus 2n. This multiplied by that, negative 2 to the negative n squared. And this multiplied by that, plus 2 to the negative n squared, negative n gone. So this multiplied by that, negative 2 to the negative n squared minus 2n. Right. So notice this and this, they can just cancel out. So eventually you have those two. Right? You can split the sum. Here, first of all, I have n from 1 to infinity. This sum, 2 to the negative n squared plus 2n. You have this sum, minus from 1 infinity. 2 to the negative minus 2n. If you write it down into details, n from 1, 2, 3 all the way, n from 1, 2, 3 all the way, you can notice that majority of the terms will just cancel out, except the first two terms. So alternatively, by changing the index, right, we let n equal to, if we let n equal to I minus 1, right, that's also fine. N starts from 1. I should start from 3 to infinity. 2 to the, so negative n squared becomes negative I minus 2 squared. Negative 2n becomes negative 2 I minus 2. Right? So negative I squared plus minus plus y plus 2y minus 4 plus 4 gone. So negative I squared plus 2y. Right. But if you change I into n consistently, that's also fine. Again, we replace n from 3. Negative n squared plus 2n. Right, this is legitimate as long as you change it consistently. So again, this becomes that. So consistent, we have this same form, except here we start from 3, there we start from 1. Right? So all we have to do is to take out the first two terms. Then from 3 onwards, can cancel out with this whole sum. Right? So we just have to work out the first two terms. N equals 1 and 2. Negative 1 plus 2. Negative 1 plus 2 plus. N equals 2, you have negative 4 plus 4. 2 plus 1, exactly 3.